All right, so today we're going to keep going in computer vision, finish it up, and we're going to talk in particular about two things: image features and object recognition. We talked in the first lecture about kind of the more basic processing of images. Now we're going to talk about what you can do with that. So once you have things like gradients, what can you do with them that's interesting, that again helps us kind of understand what's going on in an image or going on in a sequence of images. And to introduce this, and then I'm going to talk about object recognition. In particular, we're going to talk about face detection, which doesn't seem as impressive anymore because now everyone's phone does it. You can hold up your phone and it'll find faces, but we'll figure out how that works and how that actually is done, which is still pretty cool how it works. Okay, so let's jump into image features. Before I start though, were there any questions about any of the material last time? Or I guess the midterm, though, probably more on that, I imagine. One thing I took up people asked was that how you go about getting changes to your grade on the midterm if you think there was a mistake. I'll post some Piazza as well, but just fill out a little sheet of paper with your rationale on it and give it to one of the TAs. And that should be plenty. Yeah?
Was that one question that was kind of funny? Are you giving everybody points on that?
You should do it individually, probably, but just because it's really only A that's the right answer. So if you answered one of the other ones wrong, and I don't think we track people's answers, so just do that. Do that if you did that too. Just say, hey, my answer is A, and then there won't even be an issue with that one. Yeah. Okay, so let's jump into the actual content then. Image features. And we're also having a return of some class polls today. Finally, having a multi-part lecture, you have time to actually formulate some of these. So, all right. Okay, so let's talk about image features. And an image feature is a little different usage of the word feature than we mean in something like machine learning. So in machine learning, features often meant just the vector of features that would describe the input. In computer vision, a feature typically refers to an actual point in the image. Okay, so a feature is something right there. It's a point in the image, and maybe some additional information that describes that point. But that's what I mean when I say feature in the context of computer vision. So in some sense, what makes a good feature, because every point in an image could be a feature, right? But some are not as good as others. Informally speaking, what makes a point a good feature is if you can look at a little patch of the image and figure out where that is in the image. Basically means they're easy to identify in some sense, though I'll define it more formally in a second. So if I gave you this patch here, where is that in the image? Exactly, right? You don't know. Somewhere in here, but I have no idea where. Same here. It's probably in the sky somewhere, but I don't know where it actually is. What about this one? Where's this one? Yes, somewhere here, right? It's along that, but we still can't actually figure out where it is. It could be anywhere along here, and we don't really know. This one's a little harder to see. This one here is here somewhere on the edge of that building. But again, very hard to know where it is. In contrast, think about this one here. Where's this one? That's the camera lens, right? And this one, a little harder, but you should be able to figure that out too. I think it's down here. Not that it really matters, but it could be this one, but I think it's this one. It's a little bit, the angle here is a little bit better, right? But still, the point being that when you see these two, you're able to identify kind of where that is in the image there. So these somehow, in some informal way, kind of describe or are more indicative of the image than these things. Or at least are more helpful to us in determining what that image is, maybe, or finding information out about that image. So what makes a good feature, to quantify this a little bit more, is, well, one possible, I mean, there actually are a lot of answers here. And I'm going to describe one framework for doing this. There are a lot of more, and I think actually now more advanced frameworks. But one possible answer is to say, well, look, if we take a little patch around that image, okay? Or sorry, around that point, the point where we have a feature. We take a patch there, and we shift this window over. Okay, so we take this thing and we look at it now over here. If we do that, and this shifted window looks very different from the original one, that in some sense is kind of a good feature, right? That's a good point, because it means that a little change in the point affects a lot about what the patch looks like. Okay, whereas these points here, say they're somewhere here, a little shift would no longer change what it looked like. It would look pretty much the same if you shifted it. Similarly with the edges, edges are actually kind of interesting because you can shift them this way and it would change how it looks, but if you shift it up and down, that won't change how it looks. Okay, so some notion of a feature, at least how I laid it out here, is that if you shift it in any direction, regardless of what way you shift it, the image in this little patch changes. Okay, that's what we mean, or at least that's one interpretation of what it is to be a good feature for describing points in an image. Okay, so let's get a little bit more mathy now. So we're going to go back to this notation, this notion of almost out of the big chalk, which I kind of like, but I'll try to keep writing with these little stubs. We're going to go back to the notion of images as functions, right? A function of x and y. And these can be, pixel counts, or they could be fractional values. Doesn't really matter. They're kind of arbitrary. But this is our image here. And mathematically, what we want to do is we want to consider all the pixels in some window. And the way I'm going to write that is the window is W. And if I want to sum over all x and y, I'd sum over all x and y that are in W. Okay, that would be all the pixels in some window. And a window just means a little block around some center point, say centered at our desired feature. So now what we're going to do is we're going to find this function e. E is defined by the window size, but e is really a function of this displacement delta x and delta y. And e, delta y, EW of that, sorry for the little writing here, it's exactly after that thing, is the sum over all these things. If we take the image and we subtract the image shifted, where our sort of the points on our image are shifted by this displacement delta x and delta y. Can the camera get, sorry, is the camera getting all the board here? Yes. Okay. We take this whole thing and we square it. And that captures exactly that kind of intuition we were talking about before, right? It's if a little shift in the image makes a very different image, we expect this to be relatively big. Whereas if we're in the black shirt, shifting this a little bit won't change anything at all. It'll still be very low. All right, so intuitively, if this thing is big, whatever big means, if it's relatively large, for even fairly small displacements, delta x and delta y, but importantly, displacements in any direction, right? So we can actually displace x or y, delta x or delta y in any direction. That corresponds to sort of saying, we want it to be big in this direction, but really want it to be big in every direction, to have some difference there between the image and the shifted image and the original image. If this is big for all these displacements, this window, in some sense, or the center of the window maybe, is a good feature, right? It's somehow locally indicative of something in the image, because if we change it all, things change. Or if we change this at all, the image looks different. Yeah. So a checkerboard, right? So let's see a checkerboard. A checkerboard like this. So the features the checkerboard would pick out, and I think you have to sort of think about the right scale here, and scale is going to be an issue. This comes up later. So in a checkerboard, if you take this point right here, if you move that at all, it will change, right? Take a point, and here it won't, and there it will. So actually, these features, the method I'm talking about here was originally called corner detection, not feature detection, but I think features is the more general term that people use now. But it is doing the right thing. It's finding points in the image that are somehow indicative of this thing, right? So it is getting to it. I think some small differences are actually exactly what I'm asking about in a second. about why this might not be the best thing to do. But what we're talking about here is that at least if you look in a local window, these points here are somehow indicative of actually what's happening in an image. They're more relevant this point right here than like this point or this point, right? Okay. So now we do sort of the math. Okay, so this is our definition. We want to find points like this. How do we actually find it? Right? I mean, we could just basically look at all possible, loop over all possible things like this, compute all of them, and see that it's big for all of them. That's kind of a lot of computation, right? We have to loop over all possible displacements, fractional or otherwise. I guess you might want sort of fractional displacements as well. You might want to blur the image first, like we talked about before, because oftentimes, if you had like a very textured surface, that probably isn't a great feature, but you might want to, blur it first so you don't pick up that texture. Things like this. So it's a little bit cumbersome to try to compute, what's a good feature just by trying out a lot of things. We want a little different way of doing this. So now we're going to use this notion of image gradients again to figure out how we can or at least approximate this more accurately. Or not more accurately, but more efficiently, I should say. Okay, so here's the big slide of all the math, but don't worry, it's actually all very simple. I'm just writing things out very, very detailed. All right, here's the basic idea. We have our function f, x plus delta x, y plus delta y. By the chain rule of calculus, we take or sorry, not the chain rule, essentially the Taylor expansion, I'll call it. It's related, but a little different. By the Taylor expansion, this thing is approximately equal to, not exactly, but approximately equal to this function evaluated at f of x and y, plus the derivative of f with respect to x, again evaluated at x and y, times delta x, plus the same thing, the derivative with respect to y, delta y. Okay, that's just the first order Taylor expansion of this function using its derivatives. Okay? Now remember, these things, they're being called functions here, but these are just the image gradients, right? These are just other images that we get that we're writing as a function because sort of in some sense they are really functions. But if we actually want to compute these, we just take our Sobol filter and convolve the image with that filter, and then we have this thing. Right? This is our image. This is the image once we convolve it with a filter. This is another image convolved with a different filter. So these are all computable. Okay? Now this, then, if we actually take our full functional form here, where we compute this e function, this is just f of x and y minus this thing, which we approximate now using our Taylor expansion. So what we get is if we look for, I won't write it all out here, but it's fairly straightforward. If you look for f x y minus this whole thing, we just get the sum of these two terms squared, right? Because the fx's cancel out here, so this term cancels with this term. All we have left are these things. And you can actually write this now as a quadratic function of delta x and delta y with this matrix M here, where M is just this. It's the sum over all the x and y in that window of these functions of the image gradients. Okay, and all I did here was just some algebra. If you just look at what the x squared term is like, for example, it'll just be this term squared. Look at what xy is, it'll be this one, and then this one. And then if you look at what the delta y term is here, if you just take the square explicitly, it's this guy here. All right, so does everyone follow this little bit of math here? It looks like there's a lot of symbols here, but really it's 2D linear algebra, so it's pretty simple.
We call this the Hessian of the image
It's related to a Hessian. It's not quite. I wish I wouldn't quite call it a Hessian. A Hessian usually involves second derivatives. This is actually the image gradient squared, not the second differential of the image of the image itself. They are related, though, these two things. But typically, the Hessian is a slightly different quantity that you compute with a different filter. So not this one. But they're related. And they're still easy to compute, right? Again, this is just, this thing here is just the image gradient. It's the big image. We can compute that. We take, every corresponding one there, compute these, compute that. And really what this is in some sense, there's like a lot of convolutions, right? Because we're convolving over this entire window, or rather we're summing over this entire window W. So computing this M matrix here is kind of like doing 4 different convolutions. Really actually just 3 convolutions, because this one and this one are the same. Right, so we can compute it pretty easily. I mean, as long as this window's a reasonable size, yeah.
So this df dx, would that be the result of one of the differential filters?
Yeah, exactly. So going back and then sort of splitting the lecture in a bad point, but remember we talked first about how to compute image gradients here. The way, the naive way is just to have take a finite difference here. But there are slightly nicer ways where you actually convolve the finite difference with a Gaussian filter to get a smoothed estimate of these differences of these gradients. And things like this, which are called Sobel filters, are typically how you do it. So the way you actually get these things in practice is you just run a single convolution of one of these Sobel filters across the whole image. Or in OpenCV, you call this.
So you would just make a df dx image, a d
exactly.
df dy image, and then
yeah.
You assume some sort of a kind of derivative.
Right. So basically, just like this is we're calling it a function here, but really it's just an image. These we're calling derivatives of functions, but they're just images themselves. They're images you get after you convolve this thing with a particular filter that takes the derivative effectively. And that's the call to do it in OpenCV if you want to do it. Okay, so here's our matrix. We know that our this sort of error function is approximately equal to this thing. Or sorry, approximately equal to this times that. So an inner product of these two guys with this quadratic form with this guy and this matrix MW. Now the question is, can we easily say when this quantity here is going to be big for any possible inputs? And big is sort of a relative term, because obviously if these are bigger, this will be bigger. But when is this whole thing going to be big for any possible inputs, delta y and delta x and delta y? Right. So did everyone hear that? I think it's on the next slide, so it doesn't really matter. But the way you know a quadratic form is going to always be big relative to its input is if the eigenvalues of this matrix are both big. And now we don't talk too much about linear algebra in this course, so if you haven't seen this before, don't worry. Essentially, the eigenvalues of a matrix are, well, I'll define them like this, actually. It's probably the easiest way of doing it. But for a 2 by 2 matrix, at least, the minimum eigenvalue would be equal to the minimum of all x with norm, well, I'll just say, of all x with norm 1. The minimum of this thing, this equals the smallest eigenvalue. And the maximum of it is the bigger eigenvalue. People often won't actually order them this way, so that they'll sort of say lambda 1 or lambda 2 could be bigger, it could be smaller. But essentially, the eigenvalues just correspond to what's either the maximum element you can get, again, with this thing being, this x term being constrained to have norm 1, or what's the minimum element you can get with it being constrained to have norm 1. So the breakdown here is that if both of these two things are big, then you can't get a small error here no matter how you choose x and y. Okay? And that's much easier to check. Just the eigenvalues of this matrix are much easier to check than, say, trying all possible rotations and seeing which one's the biggest. That's what they're actually doing, effectively. They are effectively taking all possible sort of directions you could pick for these two things and seeing which is the smallest and what's the largest. But if they're both large, then you know that no matter what direction you pick for delta x, delta y, this thing has to be large, this whole thing. Again, where large is relative, of course, to the size of these inputs, but we're talking about kind of some relatively small displacements anyway, because we're sort of using a first order expansion anyway at the very beginning. All right, so that's the key here. So the way you do this is we know that we want to find patches where this thing is small, where this thing is big for inputs in any direction. The way we do this then is we compute eigenvalues of this matrix M of W. And if they are both big, that is a good feature. If they're both small, actually, so this should have been my test question, actually. So let me go back a few slides. If you do that with this patch here, what do you expect of the eigenvalues of that matrix? Will they both be big? Will they both be small? Or will there be one big one and one small one? So here they'll both be small, right? Because no matter which way you move, this error is always low. What about this one here? Right, exactly. Because if you move in this direction, there's very little change. That's the direction corresponding to the smaller eigenvalue. Whereas if you move in this direction, you have a big change. Here, you'll have a big change in both directions, so both eigenvalues are going to be big. And this sort of speaks well to when these things were invented. Because the first suggestion for how to use these things was actually some complex combination of this thing. So they would take the determinant of this thing minus some constant times the trace of that squared. If that was above a threshold, you call it a good feature, otherwise not. This thing here is essentially doing some odd computation with the eigenvalues. The determinant of a matrix is the product of the eigenvalues, the trace of the sum of the eigenvalues. The reason they did this is that at the time they built this, computing the eigenvalues of a 2x2 matrix is very easy, but it does take one square root operation. So when they did this, a square root was very expensive. So they actually preferred some other weird combination here to taking a single square root because this was faster on a computer. But what was sort of found over time is that, hey, look, really, it's much better to just take the minimum of these two and just go ahead and compute the square root. And now, of course, computing a square root is an instruction on most floating point processors, so it's no slower than anything else. But in the 80s, it was actually, they had to be more complex because they didn't have enough clock cycles. So these go by the names of Harris corner detector and the Shitamase corner detector. They are typically referred to as corner detectors, not feature detectors, because these features are in some sense corners, right? They're sort of looking for corners in the image. Corners are the things that are exactly those things that whatever direction you move in them. Doesn't matter. You will have a big error regardless of which direction you move your window at a corner. Whereas as an edge or a smooth patch, then you won't have a big error in every direction. So that's all it really is. And here is, if we take our image and we run this Shitamase corner detector, expect 50 of them. I should also mention that there's one more step people usually do, which is like most of these things, if you have an image and you center around this point, this will be a good point. If this is a good feature, so is this one, and so is this one, and so are things right around it, because you're looking kind of a big window around the thing anyway. So usually these things will be followed by a step of this non-maximal suppression that we're used to. Essentially what you do is you always find kind of a locally the best feature here. So if you're at a point and it looks good according to this measure, but one of its neighbors looks better, you just go to that neighbor, and you keep doing that until you're sort of at a peak, and then that becomes your corner. It's also common to not accept features that are within a certain number of pixels from each other, because you just start getting too many in a really dense bunch right there. So for example, I just happen to know the fourth parameter here is how close two features can be from each other. These are kind of details, but they are kind of relevant in the application. Because if you just looked at the eigenvalues, or the minimum eigenvalue of that MW matrix at every point in this image, you would see a lot of things that are good here, a lot of things that are good here, et cetera. And you don't want to pick all of them in sort of one little area. You want to spread them around the image. But this is the set of corners that's extracted from this image. And we can also do our little demos here. So let's look at the corners. So I'm showing now the corners in this image. So can everyone see? Are they highlighting? OK, yeah, good. So they're jumping around a lot. Certainly, they're not perfect. I try to get so if I make a nice corner with my hands, I can get a few, but I don't always get them. They're not perfect, but they are kind of the things you expect, right? If they were sort of big, that light up there looks very different. This light right up here looks very different from what's around it. So it's picking those two corners very well. It sometimes picks this one up here. It's a little bit less of a contrast, so it doesn't always do it well. But the nice thing is here is I mean, look how fast this is, right? This is essentially real time. I mean, most of the time is spent here just taking the video. It's not spent actually computing the corners. It would be the same speed if I was not computing corners. So this is a very fast operation that can be done in real time on video to detect the relevant points that you might want to use in that video. OK, so back now to one of our first quizzes. Not first, I guess one of our first in a long time. So this is only a conceptual question, and this actually, you shouldn't think for this more than 15 seconds. So I'm going to close it quickly. But the basic question here is, I justified features as being things that you could look at and place into an image. OK, and the question is, does this accomplish that? If you have an image, do you expect, or sort of think about, sort of don't think too outside the box here, but sort of think of enough images as you can. Do you expect that to actually? Oops, I'm showing. Help me to show the votes here. Do you expect it to be able to find patches that are actually good at being able to essentially, if you are given a little patch around those points, do you expect to be able to say, yeah, that is right there in the image? OK, and we'll stop after 2 minutes here, because this shouldn't take too long. If you're thinking about it too much, you're thinking about it too much.
What do you mean by produce image patches? Does it detect corners?
Yeah, so it takes corners, and consider like a little patch around that. So it takes a point in the image. Consider a little patch around that image. I motivated features saying, if you look at a patch around that, I mean, if you look at a pixel, you can never figure out where it is, right? But if you look at a little patch around that pixel, can you tell where that is in the image? Yeah. I don't know. I would just try. Refresh it. Yeah, just try refreshing. Or log out and log back on your phone. Or I mean, you can try logging on the web version too. This ends up taking all the time, unfortunately. All right, and once it hits 2:02, we'll stop for a while, knowing that apparently probably most people that don't vote are actually just because the app isn't working. Do it now. All right, is anyone still struggling to vote? Okay. All right. Maybe attendance has really dwindled down to that much. Was there really only 34 people that have voted? Could be. Okay, did you manage to vote yet? And you did too? Nope. Okay. All right, I'm going to cancel this one, and I'll give you forgiveness on this one question. So we'll just send a note or something. Okay, so I think I'm guessing. Oh, that's just pretty evenly split. Okay, all right, so the answer is no. The reason for this is exactly actually the example that we gave before, the checkerboard. So it might have been the question wasn't phrased properly, but just to sort of emphasize this point, these features are not globally recognizable. So if you have this image, right, checkerboard image, this is going to be identified as a feature. It's perfect, right? You could not ask for a better corner than that. But if I showed you a patch with this thing, it looks like this. You don't know, I guess I need to draw another one, but you don't know if it is here or here. They look identical in the actual image itself. So they are good features. You couldn't almost do better in an image like this, in some sense. You can't do any better. But they are not globally recognizable because there's going to be some ambiguity fundamentally about whether that one is here or here. In fact, I would argue you really couldn't have globally recognizable features from something like this. Yeah?
Yeah, but you're saying in general, and then you're presenting a special case of a checkerboard.
Well,
if
so
you looked at your webcam, most of those points you're detecting, it's something that you would be able to detect in the image, versus your example of a non-globally recognizable feature, which is a patch of gray or a patch of black.
I guess we're debating about the term what in general means. I would say that means this, like, does this return things that will be globally recognizable for most images? And the answer is certainly is it can. But what this thing is fundamentally doing is finding things that locally, if you move them, they will change, right? So there's nothing global about this corner detector. It's not looking for anything that sort of signifies global significance in the image. It just looks locally and says, does this look like when I move it around locally, does it actually change? Don't worry too much about the quibbles here. It's sort of, there aren't that many of these, and we count them a fairly small amount. So I really wouldn't worry about that. But at least the underlying point's important here, right? So the underlying point is these features you get, they are fundamentally local features. So you do not expect to be able to fully locate the patches surrounding features unless it just happens that there happens nothing else that looks like that in the image. But there could be. I mean, there's something that prevents there from being something that looks like it in the image.
Well, what kind of image recognition would find a global point?
I would say you can't do it. It's impossible, right? There's no feature there that's a patch that's globally localizable. That's that at least. Okay. Okay. So one last thing before I move away from features is I want to at least make a mention of a set of features that have become much more popular than Harris features, which are called Sift features. Who here has heard of Sift features? Okay, great. So essentially, a problem of the Harris corner detector or the Shitomase feature corners are that these are, while they are invariant to things like rotation, right? If you take a corner and you rotate it, that will still be a corner. But they aren't invariant to scaling. And the way to see that is that if you have something that looks, suppose that this guy here was actually like a little bit smooth, right? If you zoom way out from this could be, and you have something like this, right? If you zoom way out, this is a nice corner, right? Whereas if you zoom way in, you'll have something that looks like this. So like this is this little patch right here, zoomed in. If you do that, then there may be still some curvature, but it starts to look like something that is no longer a corner anymore. And that can be a problem because oftentimes in images you want to detect, this is sort of a trivial case here, but in images we think of being able to detect, a hand, whether or not it's right in your face or whether or not it's kind of far away. So think it's a hand. So we want image features and properties that actually can be invariant to scaling. Okay. Now now Sift was one of these. It's proposed by David Lowe. The paper's in 2004. And essentially what it does is it runs something that's actually a little different from Harris features, and Shitomase features, but it's not that different. But it computes something like the same thing. It just does it at multiple different spatial scales. So basically, it effectively shrinks the image and computes them on a shrunken image, and then on several different sort of shrinkages and growings of the image. Okay, it computes them on all these scales, and then it returns all these points that it finds as corners along with their respective scale. So for example, right around this person here, there's a great feature, because if you zoom way, way out, this person is like the one thing in this image that actually looks like anything. He just sort of looks like a little line here or something on a background of gray. So everything else is kind of washed out, but this person's a great feature. When you zoom in, of course, the person's a horrible feature. It's just black. And so what this shows here, if you can see it, is essentially the different features it finds along with their spatial scales. Sift also, in addition to just giving you the locations of features, also gives you what's called a descriptor. And descriptors are more like what we think of in machine learning as features. They are fixed length vectors that describe, in this case, those points that are labeled as features. What these are, in the case of Sift, effectively, is these are histograms of what direction the gradient is pointing at points around that point in the space and for that scale. I think the lines here actually show kind of like one of the major directions is pointing. They're a little hard to interpret, but these are sort of the a one variable description of this 128-dimensional vector describing it. And these things have been found to be extremely useful for doing things like image detection. So if you want to detect this same person in a slightly different situation, you can use the Sift features along with their descriptors and match them between the two images. And that is an incredibly effective way of identifying if this person is in another image or not. Same with sort of general object detection. These features are very, very valuable in extracting useful information from these images. It's also sort of historically a great story because this paper, I was looking it up today. It's 10 years old. It has right now 27,000 citations. And he had a horrible time getting this published. Basically, when he was trying to submit it for the first time, everyone thought it was worthless. It was uninteresting. It took him 3 years to even get a conference poster out of it. And then he finally got a journal paper published 5 years after that. And then by the next year, it was the most cited paper in all of engineering. So this is always held up as the example of how the reviewing system is broken in academics. So it's a little side note that's not really relevant to this, but clearly been a useful thing that was not appreciated by the 3 people that just were chosen to review the paper the first time. Okay, so now that we talk about features, I'm going to talk about one thing which is a little bit different from features, but relates to them, at least the way I'm going to describe it. And this is the notion of tracking features now in video. And we're going to talk about in particular optical flow here. Are there any questions first about that first part? Okay, so now we have a problem. The problem is we have a bunch of features in the image, but now we have, say, a video, or maybe we have 2 different images. We want to find, how do those features move from frame to frame? The way we're going to do this mathematically is we're going to consider images now, video, rather instead of images, we're going to think about video, now as a function of 3 inputs. A function of the xy location and time. And just like the actual numeric values here are arbitrary, I mean, we're calling them like pixels, but they don't, they could be fractions. It doesn't really matter what they are. Same with time. I mean, time is just something that, it's more at a later frame in the video, but it doesn't really matter what the delta is exactly. So all these deltas here are in some sense kind of a little bit arbitrary, but we're still going to think of them in terms of these 3 input functions. So the basic problem now of feature tracking, and I'll describe it in the context of feature tracking, though you can of course apply this to any point in the image you want to. But in the context of feature tracking, our goal is to find, essentially we believe that there's a point in image 1 that looks the same in image 2. It's just moved a little bit. So if we have a corner, right, in image 1, right, we think that this thing is the same. It's just maybe moved a little bit. So it's moved from here to over here in image 2. So it kind of went in this direction maybe. Right, that's our belief about the nature of how images move. Now, of course, they can change in other ways too, right? You can have lighting changes. You can have distortions that aren't sort of just linear motions. But we're going to talk about finding sort of a linear displacement such that this relationship holds. That's what we want to find. So the question is, how do you go about doing that? And it's actually remarkably similar to how we went about finding good features. So how does this work? Again, I won't maybe write all this on the board this time, but trying to point out the main points here. The first thing we're going to do is we're going to, again, take the Taylor expansion of this series. So we're going to say that this displacement, now we have a displacement both x and y and in time, where again the units of delta t are not really necessary here, or not really relevant here, but you have some displacement in x and y and in time. This is approximately equal to the original function plus the image gradient with respect to x times delta x, y times delta y, and then the image gradient with respect to delta t, with respect to t times delta t. So there's one more quantity here, which is this thing that we haven't seen before. These again are just the image gradients evaluated at that first time. There's nothing different about them. They're just exactly the same image gradients we had before. And this one is just a time gradient essentially. So for images or for video, all this would be is just be a finite difference, for example, between two successive time steps. All right, so you just take the image at time 1, subtract the image at time 2, subtract the image at time 1, and that would be your derivative here. Now, again, just like for gradients, we liked to smooth them a little bit. You can do the same thing for the time. So you can take multiple sequences of time and kind of smooth them together to get a better estimate of this gradient here. But it's just think of this as a difference. It's a difference between image 1 and image 2. So now what we're going to say is we want to find, remember, we wanted these things to be equal, right? We wanted this thing to be equal to that. In other words, we want this term here to be equal to 0, right? Because in order for this to be equal to this guy has to be 0. Okay, so we just want to find delta x and delta y such that this is equal to 0. Delta t is assumed, we know. I mean, delta t is always one step forward in time, whatever units we want to use. One frame forward. And we can write this a little bit, and because delta t is kind of arbitrary here, it's actually more common to just divide by delta t, this whole thing, and write these quantities not in terms of just the displacement, but actually displacement over time, which are kind of like the velocity fields, right? So that these u and v here are just delta x over delta t, or delta y over delta t, and those correspond essentially to the velocity field of the image. Okay, so we want to find, and I'm going to call them u and v. We want to find u and v such that this equation here holds. Okay, now what's the problem with that? Well, we want to find u and v such that this holds, and we can't actually do it, because for this to hold, there are two unknowns and just one equation. What this actually corresponds to is the fact that if you just look at a single pixel, you cannot tell what direction it's moving in. So think about there's sometimes called the aperture problem, where if you just sort of take a very, very narrow look and you have some line there, and in a pixel, all you can really think of is a line because it has some sort of gradient there, but it's just basically the gradient at that place. It can change from this, say, to this. Right? I should have it be linear here. You can go from this to this. But you can't tell fundamentally if this is due to a block like this. Let's see. Let me draw that a little simpler. You're just seeing one little pixel here, and it goes to this. You cannot tell if what's really happening here is that you have something like this, and it just shifted over. That's very valid. That could happen. But it just is likely that it could be something like this, where you started with this thing, then actually what happened is it moved down here. So essentially, if you look only at one pixel in the image, you can get some information about motion by looking at the gradients, but you can't actually resolve the full 2D motion of the underlying image. Okay, and that's exactly what this corresponds to here, is that if we look at one pixel, we only have one equation. And we have multiple unknowns, namely the x and the y components of the velocity field. So the thing we do, which is just like what we did with the edge detector, is that this is a technique called the Canadi optical flow. And by the way, that's Takeo Canadi. He's over in robotics here. He's named after a lot of things in computer vision. Or actually, sorry, a lot of things in computer vision are named after him. He developed them. The idea here is that just like we did with looking for image features, we looked at a small patch around a point, right? And we took sort of like this average of sort of displacement in this whole patch. We're going to do that exact same thing here. We're going to look at some window, say, around our point we're trying to track. And we're going to try to find we're going to assume that the flow field within that window is the same everywhere in that window. And we're going to see, can we find a u and v that minimizes quantity here? a single UMV that minimizes quantity. Now this is a quadratic problem. It's actually a least squares problem. So we can solve it with a single matrix inverse. Actually, even cooler than that, what turns out is that if you look at the quadratic term in UNV, so if you were to write this as, UV times the matrix M times UV, there's also going to be a linear term plus, B transpose UV, etc. But if you look at this term, this matrix here is actually the exact same matrix, the same MW matrix that we had in the case of corner detection. It just is. It's essentially this term, the term that multiplies this squared is this thing squared. This squared is this thing squared, and then the cross terms are this times that, which is exactly the same form, because this is for a fixed t. The t doesn't actually matter. It's as if you're using a single image here. So what's very cool here is that the points which, and I should also say, if this thing has two high eigenvalues, what that corresponds to is that this function having a well-defined minimum. Whereas if one of its eigenvalues is very small, this function does not have a well-defined minimum. It can kind of, be small for a whole range of different points. What this corresponds to exactly is the fact that if you have an edge, trying to track an edge, not a corner, trying to track an edge, you can't actually resolve what direction that edge is moving for exactly the same problem here. You can't figure out what direction the edge is moving. The things that are easiest to track in optical flow are exactly the points that we're detecting with this corner detector or feature detector. So, let's see how this works. I have the next. Okay, yeah. So, right. A few tricks. So, this approximation we made, that Taylor expansion that we made, this is valid at a relatively, at the level of like individual pixels. That's sort of the scale we're talking about here. So, if we have motion that's much bigger than that, it's going to be a problem. Right? We're not going to be able to track that. The thing to do then is actually to compute multiple optimal flows at different scalings of the image, essentially look for the most likely one out of all the different scalings for every different point in the image. Again, using kind of like one of these non-maximal suppression if you want to do that, but you can do it in a lot of ways as well here. When you do this sort of for real, you probably want to use more than just 2 times to track points. You want to kind of keep a continuous history of how these points are evolving over time. And finally, you also probably want to, you saw how much those points were flickering when I had my Shitamasi corner detector. You probably want to add and remove points as you go to make sure you have a nice set the whole time. But again, as with all things, OpenCV has a single call that does all of this. Actually, it really only does this one. These two you have to do yourself. But essentially, it will say, oops, I wrote corners here still. I was copying the wrong stuff. This is sort of P2, I guess, points 2. If you pass an image 1, image 2, and then their points, it'll compute how they evolve. So if points, here's a list of points that you're trying to track in the first image, then this thing, which I'm calling corners, but it really should be points 2, is the list of points, list of those same points, or it's trying to track those same points in the second image. So to see how this looks, all right. So here is a couple points. Actually, this is not great light conditions. So we'll see how this works. We'll try the more robust version in a second. But there's a bunch of points there, and the easy thing for me to do actually is actually just to move it. And the lines here in this image now correspond to the directions that it feels the points are moving. So if I see, it can't mess up. So if I rotate it, they'll kind of shift over. They'll rotate a little bit. If I move it like this, they'll kind of go left or right. And if I move it up and down, they'll be going up and down. This is just tracking now frame-to-frame optical flow, so it isn't that impressive because you can't really see. It's only tracking small things. If you want to do a better job, actually, this is not my code anymore. This is you can do all these other things. You can do these two things a lot better. Tracking features across multiple time steps, kind of keeping a consistent history of them, and adding and then removing them, and something that looks more like this is what you get. So, all right. So now it's tracking the points here, and as I move, it keeps a consistent history of them. All it's doing is the exact same thing. It's just keeping a little more history and filtering things a little bit better than I was. And it looks, that's pretty good, right? I can move sort of like this. It tracks me. Go up and down, and it tracks me. So I can find, yeah, well, hands are always sort of hard to always get. Okay, so pretty cool. You can also actually generate the optical flow for every point in an image if you want to, but of course there you have to do some sort of tricks because, if I'm again wearing kind of a striped shirt, but if I guess it has edges, right? Not corners this time. So if I'm moving a certain direction, you wouldn't be able to tell how certain things in my shirt were moving. And essentially what that means is that if you want to try to do optical flow over the whole image, you'll have to play some tricks that sort of assume the image is being transformed in certain ways so that you can track the top there, the ceiling there. To know that that's moving is very hard, right? But you can do it, but it just takes some doing. Okay, so that's it for optical flow. Let's talk about one more thing, and then we'll be done. Talk about object recognition. This again is the problem of if we have a face in an image, how do we actually find it? Again, this is probably less impressive to show you this now. The demo I'm going to show is much less impressive than it was 10 years ago because you all can pull out your phone and do the same thing. But it's still pretty cool to see how it actually works. It isn't obvious how this works, how they can do it so fast. So let's just jump in. How do we detect a face like that? How can you look at an image and say where the face is? Now, in some sense, this is a simple machine learning task. That's all it is. You give your classifier a bunch of images of faces, and we could even scale them down. We could even scale a face down to say some constant size, which is say 24 by 24. That's the one that I happen to know these later things use, so I'll just use it here. We'll scale down images to 24 by 24. So that's not very big. That's very, very few pixels, of course. But you can still, if you were to look at a face in a 24 by 24 pixel, you could tell it was face. They look quite different from just non-faces. So we scale them down to some certain size. And then we just give our classifier a bunch of examples of faces versus non-faces. This is exactly what you did, for example, in your digit classification problem. That was actually even bigger. That was 28 by 28. So you're way ahead of this, right? So you have these images, some that are faces, some are not. You have a data set which has both of these things. And you just build a machine learning algorithm, like logistic regression or anything else, to classify them, face or not face. Now, given a new image, of course, it could be that the face you see in that image is not 24 by 24. But what you can do is sort of scale that image to all different sizes. Maybe by a factor, scaling down by a factor of 0.9 each time. So you make it a little bit smaller. You don't have it each time. You kind of decrease it by 0.9 each time, another 0.9, et cetera. Such that if you were to look at every single 24 by 24 window in all the scaled versions, so I mean, what we're doing here is some big image here. We have a face. And we have a smaller one. What you do is you take sort of all these windows here. This is 20 by 24. You look at all possible positions of these things. And finally, you'll get one that is around that face. You'll call that. Your classifier will say, yes, that's a face. Everything else will be not a face, and you'll be fine. Again, as with everything, you will probably classify a lot of things around here a face. So what you do is you do non-maximal suppression again. You say, what of all those looks like the best face? And that's your bounding box for the face. That's all it is, actually, from a fundamental standpoint, right? So what could possibly go wrong with that? Actually, any guesses what could go wrong? Yeah.
The face is too big in the window.
So the face being too big is actually not that much of a problem, right? Because you will scale it down. So you create multiple versions of this thing, so this image is now much smaller. This image is much smaller than that one, and you're looking in the same at the same size windows in all of them though. So this is a 24 by 24 block here. 24 here. So you're going to get at some level the size face that you want. That is the right size. Again, if you look at all possible windows here, all possible windows there, etc., that will get you the right size. Can anything else go wrong? That's a good point. We'll get to that in a second. But I mean, machine learning is machine learning, right? You could always just make a machine learning method that'll work for all orientations you want. I think this is there really is not a deep question here. The problem here. Well, I'll just go to the next slide. So the problem here is that it has to be incredibly accurate, right? Because there are a lot more non-faces than faces. I mean, think about every single sliding window here that is not a face. There's a lot of those. Very few faces, and you want very high accuracy with very few false positives. That's sort of a tall order. And it has to be done very, very quickly. Right? We want to be able to do this in video, essentially. You know, your camera doesn't have much processing power. It can track my faces, track faces. How does that work? Well, one thing we could do, which would actually be plenty fast, we could do all of this, essentially, maybe not quite, but pretty much. I mean, it isn't that much work. If we just built a linear classifier and did this with a linear classifier, that would probably work fine in terms of speed. But as you knew from your digits problem, you were getting 90% accuracy with a linear classifier. That's probably, I mean, that's not bad for digits. There's 10 of them. Here there's only 2 things can go wrong. So maybe we'll give you even 99% accuracy. That isn't great, though, right? 99% accuracy means that if you have how many non-faces here? You're calling much more things non-faces than faces, even with 99% accuracy. Another approach would be to use a much more descriptive set of features, like Sift features. Sift features along with their, I shouldn't use the word descriptive, because use a more, a richer set of features and descriptors. And so, for example, one of the state-of-the-art things you can do for image detection, period, is to extract Sift features from an image, look at all the feature descriptors around every point at the right scale, and then match those to an image that you know to be of a certain class. And if the match is good, then that is a good, you're a good match there. That actually works very well. That's very accurate, and it's way too slow to be practical. Sift features, they're fine. There are actually faster versions of these things, but imagine computing this on every single possible window there. That's incredibly slow. Even with some of the scale invariance of Sift, you get these really kind of slow processes that just aren't, at least, you can probably make them work better now than you could when this paper came out. This paper that I'm going to show you how they did it is now almost 15 years old. But at least back then, Sift didn't even exist back then, so you couldn't do it, period. Or it did, but it wasn't published yet. Right. So it did exist, but it hadn't been adopted by the mainstream. But it certainly was too slow back then to do. And even now, this is really expensive. You probably can't do it on a camera. It would take all the battery of your iPhone. So here's how they do it. And this is a method called Viola-Jones object detection. I think it's just about now being surpassed. People are finding better ways to do things than this. And it took only about 13 years for that to happen. So this was a really, really good method. And it was called rapid object detection using a boosted cascade of simple features. And in some sense, this paper is really just about 2 things. One is a good set of features, because linear, so just using the pixel values in a linear classifier is not enough, but Sift features are too expensive. So we need something else. This paper proposed one good set of features that were accurate, but also which could be computed very quickly. And it's about ways to speed up machine learning algorithms for the detection, at least at test time. So training you can take as much time as you want, but at test time, you want to have a fixed classifier, they can just classify the things correctly. And again, that's all it is. It's just a way of doing that procedure I described before, just a little bit faster. Has about 9,000 citations right now. Just like Sift was just a good set of features with now 27,000 citations. So they're conceptually simple, but I think what's driven computer vision to a large degree is this constraint of processing power, right? If we had infinite processing, a lot of these things would be pretty easy, but we are constrained. And so some of the biggest advances in computer vision have really just come from the ability to do these things very quickly. It's not a trivial issue doing them fast here. All right, so two things. Good features, fast ML. Let's go through them both very quickly. The features it uses are called Haar features. Pattern match is something called a Haar wavelet, but these are not actually wavelets. So these are just called Haar features. And if you see them in a book, they'll say, these are Haar features. They look like this. And you'll say, well, what is that? When I first saw this, these are the features we use. I didn't understand what that actually meant. What these are codes, essentially, for how you take a set of pixel values and turn them into a number. So all this means is what you do is you take these images here, and you slide them over your image at different scales. So you could have one that spans the whole image, one that's very small. But all you do is you take the pixels in the white area, you add them all together, and subtract the pixels in the black area. And that is your feature. All right, and you can imagine this is actually pretty useful for faces, right? Because if you have a face with two eyes, right? If you look for like this feature here, and you look at these pixels minus these pixels, right at the eyes, it's a pretty good feature, right? That tells you a lot about a face. If right there, by the way, there's a difference in those two quantities. Similarly, actually a very good one for the nose. This line feature here is very prominent on the nose. I didn't draw noses on my little guys here, but if there's a nose here, and there's a difference between this, this pixel and these pixels, I'm just scribbling on a person's face at this point. You can imagine that would be a very good feature. I have an actual slide of it in a second, so I'm not worried too much. But that's all it is. It just says, take the sum of certain pixels and subtract out the sum of other pixels. Okay? And do this sort of at all different scales you can, and at all different places in the image you can. And those typically are much, if you sort of create all possible ones here, which, by the way, there are a lot of, if you create all possible ones here, these are typically much better features than just, say, the pixels themselves. So they're not quite as good as Sift features, but they are pretty good, right? One question, though, is that, well, this seems OK, but this still seems a little bit computationally intensive, right? Every time we want to compute a feature, we have to take all these values, sum them all up, then all these values, and subtract them all off. Especially if these things get the size of the actual image itself, and we want to do all possible sort of shifts and all possible sizes of these things. Even in a 24 by 24 image, that seems like a lot of computation. So the reason why these became so popular is that there's a very clever trick you can do to speed that up a lot. And these are called integral images. So the basic idea here is very simple. If you have an image here, so I'll have my little, I'm not going to draw this because I can't, it's very hard to draw the integral image. But if you have an image there, and you form some new image here, where this point here in the image is the sum of all these points. Just the sum. This is called an integral image because it's sort of integrating the image as you go forward. If you do that, you can compute the sum of any patch in this original image using 4 operations, or 4 accesses to this other image here, right? All you do is you take this point plus this point minus these 2 points in the integral image. That is the sum of every point there. Does everyone actually see why that is the case? OK. It's a clever trick, right? You also can compute this very easily because it's just one pass in each direction. It's a cumulative sum operator, so you just sort of keep adding up things as you go. It's sort of one of the more basic possible forms of dynamic programming is actually what it kind of boils down to. But it's a very clever trick, and it means that we can evaluate these HAR features at any scale. So it doesn't matter, how many pixels. We can evaluate one like this, right? Again, I'm scribbling on images here, but we can evaluate this using, I think it's like 9 because there's some actually double up here, but I think it's like 9 total operations, total accesses to memory to compute this whole thing over the whole image at whatever scale we want once we've computed that one integral image. And remember, one thing we're doing in our machine learning methods, we're scaling down the image at multiple scales, right? So this is very useful because we can compute these features not only at sort of the raw pixels, but we can compute them at higher scales too, without doing any other sort of computation. We just compute this one image and just do operations in it. That's a very cool trick that really sped this thing up a lot back when it was first described. The other trick is, well, it's great that we can find them fast, but there's still about 180,000 different HAR features you can form on a 24 by 24 image. And they are not all relevant. Most of them are complete garbage, right? It doesn't really matter if there's the rectangular sum, in this little corner here probably is not very important. So what they did is they used a method called boosted decision stumps, which are like boosted decision trees. They just a stump is a tree with one element. So you just essentially look for the feature that is most indicative of the thing being a face or not a face, and then you use an algorithm called AdaBoost to try to, or AdaBoost, to try to build a series of these things that when applied in sequence can actually classify them very accurately. What this does effectively is it actually reduces the space features you need to consider from 180,000 to like 5,000. And then finally, what they do last is they also developed what was called a cascade of classifiers that essentially has a first sort of quick pass classifier that is not very accurate, but it can easily throw out most of the examples by only looking at a few features. So it looks at like 5 features, and it says if it doesn't pass these ones, there's no way it could be possibly a face. Then the next one in the line, if it passes this first one, it will test it on the second one, which now looks at more features, looks like 50 features. I think it's actually less than that, but like say 50. If it passes that one, it goes to the third one. This one finally, I think there are a few more, but this one finally looks at all 5,000 of these, and then if it passes that, then yes, it's a face. I guess it says further processing here, but really at the end, at some point you call it a face. Whereas if it fails any of them, you reject it. The idea being, of course, that these take much less time to compute because you can just compute only the features you actually care about that you need for the early stage classifiers and do a much better job that way. So that's how face detection works. And now, let's have one more little quiz here. So this is a question now. Suppose I train my classifier with these 4 images, and a lot more like them, but I didn't want to keep taking pictures of myself. And this is a little bit informal too, but there are multiple possible answers here, but there are 2 at least right answers. The question is, if I train things like this with, I should say, with a HAR cascade, which of the following things do you think I could classify correctly as a face? And the thing to think about here are the features that it is actually using. Think about those. And think about if I give it this kind of training data, what could it do to detect those things? Or would it not be able to? And this is A, B, C, and D. up, so I want to see the total votes as they increase too. Everyone, by the way, sees what I'm doing here, right? I'm tilting my head here. Here I'm looking to the side. Here I'm looking at my eyes, and here I'm closing my eyes. All right, we'll go to 48. Maybe we'll actually a little past 48. I only have one slide after this. So. All right, who has not yet submitted? Anyone? Okay, I'm gonna. All right. Show results. Okay, so which we can classify? So yes, people were right on this one. So number A can't do this one very well. Now, in general, and this was actually mentioned before about rotation. In general, of course, if you were to train something like a Sift feature or edge features in general, corner features in general, there would be a problem here because corner features are invariant to rotation. But if you look at the har features in particular, those are absolutely aligned, right? They are things like this. This here detects horizontal edge or detects vertical edges. The other one detects horizontal edges. You can't get around that. If you do rotation, you don't have that nice trick of the integral image anymore. So that's why they don't. That's sort of why they forego that in favor of just doing it. Now what they also actually do is just do a few rotations manually. So they actually, to do better, you can actually just take your whole thing and rotate it every way you can and say, is it a face rotated anyway? That gets around that, but it's actually pretty hard to detect that manually. Yeah. We'll see in a second if it does or not.
Actually, horizontal.
So the base algorithm will not, definitely not, because these things are hard features and they are trained to. I mean, if you train it on every single thing you can, but I'm training it on images like this. I'm training it on things the face is always straight. So these ones will always learn a detector that looks for edges which are oriented one way or the other. The side everyone pretty much got. The side there's no way to know that this is at all like this, right? And then the last two, yes, they look fine. I mean, maybe looking to the side a little bit, but the thing is, I don't have my eyes that open, some of these ones. So if it's looking at my eyes, the way it's in my eyes here, it's actually doing a pretty bad job. Same with my eyes closed. My eyes are almost closed here. So if it can't detect that, it's pretty bad. Let's just see how it actually works in the 0 time we have left. OK, here I am. Here's my face. Now what you'll see is if I tilt it, it goes away. Because it can't, because it's detected as front faces, right? If I go to the side, it doesn't do it either. If I close my eyes, I think it's still detecting me. I don't really know. But I think it is. And then if I look to the side, I'm looking at you now again. I don't really know if it is, but I think it is. So look at everyone else, too, actually, while we're doing it. See how many it gets in the class. All right, let's see. They're actually pretty far away. So look at the camera, actually. Everyone face up here. Oh, it's doing a bad job. Just one in the front there. OK. Well, another one for a second there. The lighting's actually very bad here, so I couldn't even tell by looking at that those are all faces. But for one face, at least, it's looking pretty good. So OK. So this is how your phone works. There are some modifications now, because you want to do things like rotation. But certainly, if you train it all on sort of faces that are straight up and down, it will not be able to detect things like rotation or things like turning my face to the side. You can train one for the side, and it'll work too, but you have to train one for the side. All right, so I didn't ever quit that, but all right. So last things. Computer vision is about how we understand images on a computer. It's not a simple task, right? Humans are amazingly good at this. We have amazing intuition that lets us know what's going on in an image. We've evolved over a long, long time to be able to do this. It's very hard for computers. To the point where to solve this, you almost need to solve this general AI, right? But if you want to play around with it, the last thing I would say is this is a solved problem in a lot of ways. Download a library and start with that, because you will really that like Cascade classifier was 10 lines of code in OpenCV. They have a lot of that built in. Build upon this stuff because it's very mature, and you can do a lot of cool things with it. Is that all right?